Medicine has evolved, and during the 20th century particularly, it became focused on finding a specific cure for a specific disease. Now, unfortunately, we have more or less exhausted that approach.
So what we are doing at the moment in the clinics is we are trying to treat diseases. And what we really should be doing is to treat the patient. And for that we need the individual information about that person and link it to the vast amount of knowledge that has been accumulated over centuries of medical treatment in the profession.
And that's why you need clever mathematicians, clever computer scientists, good biologists who know exactly what data to produce, how to integrate it all together. That's why we need the technology that is being developed by the Virtual Physiological Human Project.
Medicine has been evolving for centuries by studying the human body and its illnesses. Our ability to gather medical information has developed increasingly since the application of X-ray technology in the late 19th century. And later, penicillin, which has saved hundreds of millions of lives in the 20th century. The discovery of the structure of DNA led to the mapping of the entire human genome, a key step in our understanding of genetic diseases. As we continue to progress into the digital age, computer tablets are increasingly used by doctors and surgeons. Now we're at the forefront of new developments in medical technology, the virtual physiological human, a digital representation of an entire human body. But as these virtual humans are based on data from real patients, each one is unique, right down to their organs and connected systems, allowing the prediction of future medical conditions or reaction to certain treatments which could end up saving the patient's life. As the modelling of the entire human body is a complex task, the research is being broken down into individual projects all over Europe, each one dealing with a separate aspect of the human body or a specific disease. The European Commission launched the first phase of this research programme in the period 2007 to 2013 with a budget of €207 million. Investment and coordinated effort beyond this date will ensure that Europe leads the initiative and its citizens benefit first-hand from this technological breakthrough in medicine. About 40% of prospective new drugs fail to come to market due to their adverse impact on heart rhythm. One of the VPH's projects in Oxford is addressing this problem.
We were working very closely with pharmaceutical companies and also clinicians to develop these models of the heart and also understand better how computational methods can help in drug development. What we are aiming at in PREDICT is to develop safer drugs. We also are developing tools within PREDICT that would allow a better use or a safer use of the drugs that are developed, so it would eventually impact the way patients are treated and to make drugs more efficient and safer.
One of the major causes of mortality in Europe and a great expense to national healthcare systems is cardiovascular disease, costing billions of euros and millions of lives every year. This is what the VPH project UHeart is working on.
So UHeart is developing models of the heart that link proteins to cells, tissues to the whole heart in order to be able to do better diagnosis, but also to improve the design of medical devices. Failing hearts need to put in a stimulation device that stimulates the heart at particular points to improve its contraction, to give better output. And the use of personalised models can then help you design exactly where to put the leads for that individual.
Another major cause of death in Europe is cancer attacking any part of the body, the lungs being the most common location. Professor Norbert Graf of the Contra Cancrum project believes that computer-assisted prediction of the best treatment is the key to fighting cancer.
Today, treatment of patients with cancer, and especially also with brain cancer, is based on different treatment options. So if we have the data of the patient in the computer will simulate different treatment options. And these different treatment options will tell us what is the best option to shrink the tumor the most. And if we get this information before we start the treatment, the patient can get the best treatment available today. I'm really convinced as a medical doctor that this technology will save lives. And by saving lives, we will have less patients with relapses. Treatment of relapses is very costly. This will at the end be much more cost effective. I'm really convinced that the technology evolving today, especially computer science, can handle this vast amount of data. And if they build up and come up with new tools to analyze these data, then we will get new insights into the biology of tumors, and we will find new treatment options, and this will change the outcome of patients in a tremendous way.
Osteoporosis is the cause of nearly 4 million bone fractures every year, costing Europe 30 billion euros. This will double by 2050. The VPH-OP project will focus on more personal, more effective steps to prevent fractures through a better understanding of the body as a whole.
The long-term scenario, which is the most exciting for us scientists, is the ability to integrate information about the human physiology and pathology at very different scales. When we investigate the human body, we look at the very small, the atoms, the very big, the body, but no one is capable of looking the body as a whole in an holistic way. That's the long-term goal, to be able to understand how the human body works at all scales, all together working to produce this thing we call life.
At the ground level, the VPH developments will influence the practice of surgeons in many fields. For example, Didier Mutter, a surgeon in the University Hospital of Strasbourg and a collaborator in the Passport project.
The Passport project is really the development of a new virtual database of the patient, allowing the surgeon to analyze better the images of the patient before the procedure, to simulate and eventually to ask other advice concerning the realization of the procedure, and something very original during the surgical procedure, the possibility to fuse real and virtual data of the patient to optimize the surgical procedure. For the surgeon, it simplifies and modifies significantly the way of performing surgery, making it quicker and safer for the patient. All the data of the patient will be today in a cloud computing system available anywhere by anybody all the time, which is, you imagine, very important that today when patients travel so much, can see people, can see medical practitioners located all over the world, or if they have any accident, injury out of their country. Everybody will get access to their virtual clone before the new event. And that is certainly a revolution in the management of the data of the patient, and this must be increased a lot in the future.
A networked distributed computing infrastructure and the cloud are in the core of the implementation of the VPH's benefits to society. Further investment in computing infrastructure to increase capacity will enable the development of more effective, faster simulations and give citizens wider access to the benefits of the technology.
This is more difficult than sequencing the human genome, and we spent $1 billion doing that. The payoff will come in being able to treat very, very complicated multifactorial diseases, which of course are increasingly important in an aging population of the kind that we now have.
If you think of what the VPH tries to achieve, it clearly is mission impossible. But the point is that same challenge exists regardless of whether we use the VPH or computer models or do it at the back of an envelope or in our minds. The challenge remains, it's mission imperative. And without doing it, we are not ever going to bring together all the information that's there from molecular level investigations, from imaging, from clinical observations, from genetics and from the development of disease in an individual. So the virtual physiological human, one shouldn't think of it as a construct that will all of a sudden walk into a room or appear on a computer. It is a vision, a collection of data and techniques and conceptual links between them that will allow us to be better in predicting, in diagnosing and in treating disease.